Okay, welcome everybody. Um, well, no, I'll wait another few seconds. Okay, so let's get started. So in the last lecture, we talked about the basic theory of the weakly interacting Bose gas with the Hamiltonian of kinetic energy of a bunch of bosons and a weak repulsive interaction between them, short range repulsive interaction. And what we found was that the ground state was a superfluid and had a very interesting quasi-particle dispersion where there were Bose particles which dispersed linearly at small momenta and which I argued should be identified as the sound mode, which is sometimes called a second sound mode of a Bose gas. But at high momenta, you went back to the usual k squared over 2m dispersion. So today we're going to rederive that result in a different way, in a way that makes the nature of the symmetry of the problem a lot more manifest and gives you a much better feeling for where this mysterious sound mode appeared from and what its physical interpretation is. But any questions before I start? Okay, so let's rewrite the same Hamiltonian here, which is written in first quantized form at the top of the page. We wrote it in second quantized form here, and now we're going to write it as a path integral. And as how you has discussed, the derivation of the path integral proceeds by the coherent state method. You can also think of it, very easily as just in two steps. First, you start from the first quantized Hamiltonian. You write the first quantized Hamiltonian in terms of Bose creation and annihilation operators. And now you think of each creation and annihilation operator at each momentum as a harmonic oscillator. Now you know how to write down the path integral for a harmonic oscillator, and you just do the same for these oscillators. And when the dust settles, you get what's called the coherent state path integral, which is written down here. So this is now the Hamiltonian is this in the field operator representation, sorry. And the path integral is a path integral of a field, psi of x and tau. This is tau is imaginary time, and we are evaluating the partition function. And then what happens is that the time runs from 0 to beta, beta being inverse temperature here. Beta equals 1 over temperature. And there's an integral over space. And this is the form of the path integral of the dilute Bose gas. Let me just very quickly to remind you how you might derive this from the method that I just presented. Where are we here? Yeah, here. Okay, so if I, that the partition, if I did have had a single harmonic oscillator, you may have seen that the path integral in imaginary time is just some d of x of t or x of tau times exponential minus 0 to beta d tau of the kinetic energy, which will be m over 2 dx d tau squared. This is the Lagrangian, but now in imaginary time, plus the harmonic potential, which is 1/2 m omega squared x squared. Okay, so this you know from your undergraduate quantum mechanics, but we can also write it as what's called the phase space integral. You can write it as an integral over momentum and an integral over x, and then that becomes, well, this becomes something like this, 0 to beta d tau of p squared over 2m, that's the kinetic energy, plus IPX plus 1/2 m omega squared x squared. Okay, so if you here, you can just do the integral over p by completing the square, and you can come back to that. So these are the two different ways you may have seen the path integral. This is the configuration space path integral. This is the phase space path integral. And now what you do is just change variables, and that's really all the coherent state path integral is. You change variables by the usual harmonic oscillator variables, which I won't be able to write down exactly, but basically A is something like P plus IX, or no, X plus IP, or something like that with some constant here. This is the usual transformation from P and X to A and A dagger. Since we're doing a path integral, we just think of A as a complex number here. But you make the substitution, put it in here, the integral over P and X can be written as the integral over the complex number A. And this just becomes, if you work it out, you know, it's very instructive to do that. 0 to beta d tau of A dagger dA d tau plus h bar omega A dagger A. So that's the quickest way to get the path integral of a simple harmonic oscillator in terms of the creation and annihilation operators, which now have become this field, this complex field A. And the fact that A comma A dagger commutator is 1 is what gives you then this term here. So this term is really representing the fact that this is a commutator. Okay, so what we've done here is basically exactly the same thing. This was the commutator of psi inside dagger. It's a delta function. There's a few more x labels. And the A dagger A tau term is exactly psi star d psi d tau. Of course, we do this in momentum space, but then we can go back to real space. And the kinetic energy of the harmonic oscillator, which was k squared over 2m, just becomes this grad psi squared over 2m. And similarly, the potential. And then the interaction, so this is a bit more complicated now. Well, the interaction is already in that form. We just retain it in exactly the same form. Okay. So this is something how you is covered in section in a much more formal and complete way, but this is the quickest way to see where this comes from. All right, so now we're just going to think of this as a stat mech problem. We have some field psi of x and tau fluctuating in imaginary time. It's periodic in imaginary time, and we just have to evaluate this path integral. So how are we going to do that? Well, first of all, we're going to do it by the saddle point method. You know, that's really what you always do. You get faced with, once you're given a path integral, you find the stationary points where the argument up here is as small as possible, so that then this e to the minus s as large as possible, and then you fluctuate about that point. So we assume here simplicity, the saddle point is time and space independent. If you assume that, then these two terms will disappear, and you only have this mu psi squared plus u over 2 psi to the 4th, and that's the famous Mexican hat potential. So we have some potential for psi. V of psi is minus mu psi squared plus u over 2 psi to the 4th. This u is the same as u naught in the last lecture. Sorry for the inconsistent notation. And so now if I plot this v, if this is v, and this direction is psi, at least one axis of psi. So that looks something like this. As a minimum of psi equals 0, because mu is positive. and then goes up. But psi is really a complex number. So really, I should think of the psi plane. This is the real part of psi and the imaginary part of psi this way. And it's really very much like a Mexican hat. Well, I'm not doing a good job of drawing it. Something like that. Okay. All right, so there's a whole circle here of minima at the rim of the hat. Just imagine you take this shape and you rotate it about its axis. So you have to pick a saddle point, and here this is of course the key point. You're going to pick. You can pick any point. So let's say you pick this point to be the correct saddle point. Well, then what you notice then immediately is that there's one direction which costs no energy, and that's the phase direction in this direction here. Sorry, there's a lot of sun here today, so I can't see my, there's a phase direction this way. So that's going to cost no energy because you're going to stay at the rim of the hat. Whereas this direction in this variable is going to cost us energy. So we can call that the angular direction theta, and this is the radial direction, which will be rho. So we'll choose angular coordinates here or polar coordinates, where we're going to think of, let's look at the psi plane from the top. This is the real part of psi, and this is the imaginary part of psi. So we're going to pick a point here, which is at this point here. And we're going to call this angle theta. And this distance, actually, we're going to call square root of rho, not rho. Okay, so if you do that, you get this ansatz. So what is rho naught? Rho naught is the minimum value, is this position here. This distance is rho naught here. And this radial distance, that's rho naught. And it's equal to mu over u. And again, sorry for the inconsistency of the notes, because these were notes from different years. That's what I call n naught when I did the operator method. Okay, so rho naught is equal to this. That's given, and I need two variables, rho 1 and theta. And why am I writing it as a square root? Well, because the density is mod psi squared. So you see right away that the density itself, the actual density, which is mod psi squared, will be just rho naught plus rho 1. So rho is just the density, rho naught is the mean density, rho 1 is the fluctuation in the density. So at the saddle point, rho 1 equals 0 and theta can take any value. You plug this in here and expand about the saddle point. Whoops. Okay. So you plug this expansion in here and expand, well, just reevaluate. Okay, so when you do that without any approximation, when the dust settles, this is what you get. So first of all, the time derivative term is kind of interesting. This comes from just expressing, just inserting this expression here into that and just simplifying with no approximations. So you plug it in, simplify, you can integrate by parts just to make life simple, and you get this expression. So this is kind of cute because this tells me that rho 1, the density fluctuation, and theta have this conjugate relationship, because where did we see something like this before? Well, we saw it just right here. It's a very much like, oh, excuse me, somebody should have corrected me. It's not IPX, it's by PX dot, dx d tau here. There. So that rho d theta d tau term is very much like the px dot term over here. So this tells me a very interesting feature of the dilute Bose gas, which is not true in the relativistic Bose gas, that the phase of the Bose gas is canonically conjugate to the density. They're like canonically conjugate variables. Density is like the time rate of change of the phase. So these are canonically conjugate variables, like momentum and position. Then what do you get? Then the nonlinear term, so that's the beautiful part of it, the nonlinear term, which is psi to the fourth here, just becomes rho squared. Or it becomes a rho naught plus rho 1 squared. And you expand the whole thing out. And so and this is what you get. This is from the gradient term, it's probably the most complicated term. So two things to notice. First is that all terms depends only on the gradient of theta. That must be the case because the actual value of the phase didn't matter. So that's the, that's the importance of the phase. The phase can take any value and the energy only depends on the gradients of the phase. A gradient squared in real space and one time derivative in time space. Second, there's no term to first order in rho 1. You always start at rho 1 squared. There's nothing depending on rho 1, linearly on rho 1. And that, of course, is because you're expanding about the minimum. If you're not expanding about the minimum, you would find a term that depends on rho 1. Okay, so there we are. This is some kind of, so we can Fourier transform in momentum, and then the gradient just becomes k. And now you can see that this is nothing but the action of some kind of nonlinear oscillator. Well, okay, yeah, there's complicated rho 1's term here anyway. So if we just take a given momentum k, it's just very much like the coordinates of a nonlinear oscillator, but let's just expand to quadratic order. So we take these terms and just keep terms to quadratic order. This is already quadratic in rho 1 and theta. So you get this term here, and then this u over 2 rho 1 squared is this term. And in Fourier transform, you take this term, it gives you, this one, that gives you this, okay. And finally, there's this term here, of course, that's here. Okay, so this action here, everything is quadratic. It's really just a harmonic oscillator where theta is like position and rho is like momentum. Okay. So, and momentum, I mean, the wave vector k has just become being absorbed into some kind of effective mass here. So how do we proceed? Well, we proceed exactly as we proceeded from here to there, just integrate out p. If you integrate out p, you'll get, the square of this term, which is this. So this is by completing the square, you can integrate out rho 1. So if you want to see how that's done, let me just mention, where are we here? Okay, here. Okay, page. I mean, the general trick we're going to use over and over again. So when we do path integral, this is the trick we're going to see over and over again. Why is this over here? I don't know. Okay, that's funny. Let's erase that. Okay, just ignore that. I don't know why that's there. So you have some integral of e to the minus integral dx, e to the minus ax squared plus bx. So what you always do in these things is you just complete the square. You can write this as e to the minus a times x minus b over 2a whole squared. And then you got to cancel this. So that'll be plus b squared over 4a. Okay. And now you can do the x integral because it's just something that's independent of b. You can just shift x and it's independent of b. So this just becomes some number. This is equal to some number independent of b. That's overall normalization we don't care about, times e to the b squared over 4a. So this is the basic trick we're going to see over and over and over again. Okay, so I'm going to use that trick here. So get very familiar with it. So I just complete the square with respect to rho 1 and integrate over rho 1. That's here. And when you do that, just complete the square, you get b squared over 4a. In this case, b is this, d theta d tau. So you get d theta d tau squared over some mass. And then this is some thing that goes as theta squared times k squared, which is the momentum. And now this is precisely the action of a harmonic oscillator. It's precisely of this form, and so you can read off the frequency of this oscillator. So we've got one oscillator for each momentum k, and the frequency of that oscillator, if you just work it out, this is the expression for it. And lo and behold,
how did we get like exact theta dependence? Like before, everything was like a gradient of theta.
Oh, there's a factor of k here.
Oh, okay.
K times theta is gradient theta squared. I've done a Fourier transform.
Yes, of course. Sorry. Yeah.
Yeah. No. Any other questions? Okay. So we just complete the square, and lo and behold, so what we found is that there's a harmonic oscillator for each momentum k, and that harmonic oscillator, the displacement of the oscillator is just the phase that oscillates, and the frequency of the oscillator vanishes as k goes to 0. That's because of this k squared here. This is some effective mass of the oscillator, which also happens to depend on momentum. Anyway, so this is just a harmonic oscillator, and so you can read off the frequency of the oscillator, and there it is. And lo and behold, it's exactly the answer we got from the Bogoliubov theory. So it's exactly the same, and it has this form, which is linear at small k, and k squared at large k. So this shows very explicitly that this mode here is very much just an oscillation of this phase at long wavelengths. And that oscillations of this phase is canonically conjugate to the momentum. So this direction is like position, and that direction like momentum, and you know they oscillate out of phase in any harmonic oscillator. So as this thing is oscillating, the density is oscillating this way, and so that makes sense that this is precisely a sound mode. It's just a density oscillation where the phase is sort of canonically conjugate to the density. And this also explains why the frequency of the sound mode goes to 0 at long wavelengths, because there's no restoring force in this direction at long wavelengths. The restoring force of the oscillator is entirely dependent on k. It vanishes when k goes to 0. So that tells you why there's a sound mode, which energy goes to 0, and it all has to do with this independence on theta. So this is sometimes stated in the language of symmetry. So this problem has what's called a U1 symmetry, symmetry of rotations around the circle. That's what more technical word for symmetry of a circle is just U1. And that symmetry is broken by the ground state. So you pick this direction, that gives you, you break the symmetry because you picked an angle. And then associated with the broken symmetry, there's a zero energy mode, which is this case is the phonon, or the sound mode, right? So the whole physics of this is the broken symmetry. And what is the symmetry? So now you may have heard from, a classical mechanics course that associated with every symmetry, there's a conservation law or an operator that commutes with the Hamiltonian. And so that same argument here, you can ask, well, what is the operator that commutes with the Hamiltonian that gives you the symmetry? And you can see that that's nothing but the particle conservation number. So there's this one operator that commutes to the Hamiltonian. If you go back to the second quantized form, the original Hamiltonian written here, where did it go? Yeah, this original Hamiltonian, I can define the number operator n hat, which is sum on k, b dagger k, bk, and you can work out that this number operator n hat commutes with the Hamiltonian. Well, of course it does. Everything conserves the total number of particles, and it's that conservation of number which we can understand that as by Noether's theorem as related to the symmetry of the independence of anything here to the phase of the B. Okay. So that's the basic physics of a superfluid, is broken symmetry and the associated low energy sound mode. Okay. Right, and then of course, the Higgs phenomenon. You sometimes see this kind of picture for the Higgs boson. The Higgs boson is precisely actually this oscillation, and the W and Z bosons for the weak theory of weak interactions are these oscillations, but they're not massless or zero energy because there's a gauge field. So that's the Higgs phenomenon. How when you have a long range interaction, these theta fluctuations can acquire a finite. And that's what happens in a charged Bose gas. When you put in long-range Coulomb interactions, you'll find that this mode has a energy called the plasmon. And yeah, maybe possible we'll make a homework problem on that. Okay. Any other questions? So that's really all I have to say about the dilute Bose gas, and I'm now going to move on to another topic. Okay, so now you've seen this two different derivations of it, and hopefully, you'll get comfortable with going back and forth in these two different ways of thinking. All right, so we'll begin the next chapter then, which is closely related. Yes, go on.
Sorry for that. I wonder whether the patternable effective form you write down capture, for example, when the theta might have a singularity, like a vortices. Does that?
It does. It does. We're going to come to that pretty soon. So I want to do the BCS theory first, and then we'll talk about vortices. Yeah. So the vortices are going to play a crucial role when we start talking about topological phases and many other things. Yes. So right now, Joe was making an important point. We're only looking at small oscillations of theta, but you can imagine what are called vortices, where theta goes all the way around as you move around in space. So those become topologically non-trivial, and those are crucial for all kinds of non-perturbative effects and other phases of matter. But we'll get to that. We're just getting set up for that now. Okay, so let's talk about the BCS theory. All right, so I have some rather detailed notes of, standard many ways of thinking about BCS theory, but I'm going to take since you've already done the Bose gas, I'm going to take a shortcut because the ideas are really very similar. Although I should say that at the time BCS proposed it, the close similarity between their ideas and the theory of the Bose gas were not at all evident. At least, it seems kind of bizarre looking at it back from today, but when such new things are discovered, it's always very confusing in the initial days. All right, so the key to the BCS, so we also know that metals at low enough temperatures, almost all metals become superconductors, where they can transmit electricity at zero resistance. And today we understand that as the analog of the superfluidity of bosons, except we're talking about now a charged boson that condense to form the superconducting state. So that's why you can measure current. So they can carry current with no resistance, whereas superfluids or bosons can transport momentum or mass without any viscosity. Those are analogous phenomena. Okay, so the key to the BCS theory was an observation by Cooper, who's the C in BCS, that Fermi surfaces, the Landau-Fermi liquid theory that we discussed, it's all a very beautiful theory, but it's actually at low enough temperatures, we know today, always unstable. I mean, maybe ridiculously low temperatures, but there is an instability of the theory. And the instability is due to the fact that if you take two fermions in the presence of a Fermi surface, they like to form a bound state. And there's always some angular momentum channel where there's an attractive interaction. That's something called the Cohn-Luttinger effect we won't talk about. But let's take the simplest case. Let's imagine that there's a weak attractive interaction near the Fermi surface. So now say we're in 3 dimensions, so in 3 dimensions, we know that if you have 2 particles with a weak attractive interaction, they need not form a bound state. You need a finite attractive strength before you form a bound state. But what happens in a Fermi, the presence of a Fermi surface is slightly different. So what happens, roughly speaking, and we'll see a more careful calculation of this in a more general setting. So here's a Fermi surface where all states are occupied. And then you add another particle, one particle here, another particle there. But what happens is that the dominant dispersion of this particle is predominantly along the radial direction. Okay, so the particle is basically moving along only in this direction. So this is just to say that the bound state problem is very much like in 3D with a Fermi surface. Is very much like the bound state problem without a Fermi surface in 1D. So it's because electrons move predominantly just in one direction orthogonal to the Fermi surface. And we know that in 1 dimension, for non-relativistic and relativistic dispersions, even an infinitesimal potential is enough. There's always one bound state in 1 dimension, no matter how weak the attraction. And that was the basic effect, very summarized here that Cooper discovered. So let's say that is the case. So the fermions like to bind in pairs. So let's write now an operator which creates a pair of fermions. Okay, so here's our operator here. It'll turn out also when we work out the details that the bound state is a spin singlet state, that the fermions like to be in opposite spin. I mean, that's very much like, say, in a hydrogen molecule, the 2 electrons have opposite spins. So you take an electron, say, with spin down at position r minus r over 2, spin up with r plus r over 2. So r is the center of mass position of the pair of electrons. So psi here refers to electrons. These are fermions with spin a half. And g of r is their relative wave function. Okay, so this operator just creates 2 particles with opposite spin. Center of mass position capital R, so it depends on capital R. You integrate over all relative positions. Little r is the difference between them. And it just creates a molecular state. Okay, so this creates a molecule of 2 electrons with center of mass position R. Okay. So we know the electrons like to do this. So why don't we just let all of them do it? And that's basically the BCS wave function. So the BEC ground state in the very simplest case, we said, well, you have a bunch of bosons, put them in 0 momentum and take n of them. So here I have this pairs of fermion, which like to form a bound state. And I'm going to treat that pair of fermion as just some kind of Bose operator. Creates, at least when these pairs are well separated from each other, there will be bosonic. Well, let's just ignore that they're not well separated from each other, and just take this Bose creation operator, which I call psi c for Cooper. So this creates a Cooper pair operator. So this operator creates a Cooper pair centered at R. Well, I should take a Cooper pair at 0 momentum, because that's what I did over here. So to get a Cooper pair at 0 momentum, I have to integrate over all R. Excuse me, so which I didn't write down the dr over there. So this is dr. So that gives me the zero momentum Cooper pair operator. So that's completely the analog of B0 is this thing. And now we usually like to think of n electrons, not n Cooper pairs. So there's the n/2 Cooper pairs. I take the n/2 power of that. So these are precise analogs. And now I can just substitute this for this and make it a little more democratic in terms of my variables of integration. So that gives me d3r1, d3r2, g of r1 minus r2 of psi dagger up of r1 and psi dagger down of r2, and take it to the power n/2. Okay. And now I take a Fourier transform of this. So the Fourier transform of psi is C. This is the electron creation operator. I'm going to use C's for electrons and B's for bosons. Psi is, in this case, an electron here, as opposed to psi sub C, which is a Cooper pair. So this gives me that, and this gives me that. And because if you take this only depends on R1 minus R2, you'll find when you take the Fourier transform of this, you get C of K up and minus K down to the power n/2. And that is the BCS wave function. It's nothing but this wave function written out in momentum space. Now BCS originally wrote it down in a different way, in some grand canonical way of thinking about things, but we know that doesn't really make a difference. And maybe that obscured the difference between this and that, but there's really nothing. There's no difference. They're exactly the same, except for B0, you just take the Cooper pair at zero momentum. So this, if you can view as a variational ansatz for a condensate of Cooper pairs. There's, unlike the Bose gas, where we knew when this was accurate, it's not so obvious when this is accurate, and so that takes some calculations. In fact, for the low TC superconductors, it turns out to be extremely accurate, but for high TC, probably not. But it has the basic feature that there's a Bose operator which condenses, and so that similarly that would imply that there is a phase and there's off-diagonal long-range order in the Bose operator. Okay, so this is the BCS wave function. It's also instructive to write these two states, this state here and this state here, in first quantized form in the good old Schrodinger way of writing things. So what is the BEC wave function? Well, it's a bunch of bosons, each at zero momentum. What is the wave function of a boson at zero momentum? It's just one. It's a constant. So the BEC wave function is simplicity itself. You have n bosons, wave function is one. That's it. The BCS wave function is a little more complicated. Basically, you take pair of fermions with relative wave function R1 minus R2. I should say here also, we have to make, since this is up and down, basically there's some choices whether you take this an even or an odd function of R1 minus R2. The simplest case of S wave pairing corresponding to this is an even function of R1 minus R2. So if this is even under R1 minus R2, this thing is going to be anti-symmetric under exchanging up and down, which means it's really described as spin singlet. Yeah, okay, so that's just a little bit of algebra. You can rewrite this as psi dagger up, psi down, minus psi dagger down, psi up, using the even property of this. Anyway, where was I? Yeah, so what is the BCS wave function? Well, you just take first particle spin up, second particle spin down, and put it in this state. And then with 3 and 4 and so on. And then you got to anti-symmetrize the whole thing by summing over permutations. So this very complicated wave function now, which is not so easy to write in the first quantized form, is exactly this wave function. This is a much easier way of thinking about it. Or this in real space. Okay, so all we're doing is forming molecules and putting them in the very simplest BEC state. So that's a trial wave function. It may not be that great, but what is the fundamental property of this wave function? So the fundamental property is off-diagonal long-range order. So fundamental property of diagonal long range order, which is, as we saw last time, it's exactly the same as, well, let's take R going to infinity of the Cooper pair operator, psi Cooper pair dagger of R, expectation value psi of 0 not equal to 0. So exactly what we said for bosons, we now say for Cooper pairs. So that's a very precise, rigorous statement that I take my many electron state. I pick some G of R. In fact, it won't even matter much what I pick for G of R, which I take this, and then I define this operator of the fermions, this operator here, sorry, and then take this correlation function. So this is a 4 Fermi correlation function, not a 2 Fermi correlation function, but that makes it a little more complicated to evaluate. But eventually, what we're going to do is actually get a theory for this Cooper pair operator, some effective theory, which is called the Landau-Ginzburg theory, using which we can evaluate this quite easily. Another way we talk about off-diagonal long-range order, which is also sometimes a little bit confusing, but which is what we did in the theory of the Bose gas, is that we say we have a broken symmetry. You pick a given phase of the Cooper pair wave function. So we say that psi c of R expectation value is equal to some number. Let's call it psi 0 times e to the I theta. So that's, so doing that is no different from what we just for the Bose gas, but that's a different file. We'll have a, might as well draw it again. We'll have a Mexican hat potential going like this. And we just pick a point here with angle theta. So this point here is psi naught e to the I theta. That breaks the symmetry, but that's a good way to begin. That's the good way to set up the theory, because then we can do fluctuations about this state. And there is really a broken symmetry. That's what this tells you, that there's a broken symmetry, because it correlates the phase at point R to another point infinitely far away. And rather than always referring to that point infinitely far away, we can just go ahead and fix it. So when we fix the phase, we seem to get kind of a contradiction, because this expectation value seems to violate particle number conservation, because you have side dagger. So the state on the right and the state on the left have to have different numbers of particles for this to be non-zero. So it's strictly speaking only non-zero in the grand canonical ensemble, but that's fine. Even in the real system, although we may not be in the grand canonical ensemble, this is the easiest way to keep track of the fact that the phase is the same everywhere. This is the more precise way that works in any ensemble, but this is, so this thing here, we'll say the psi naught squared. Yeah, so the point is, you would like, if you take two operators, like these two operators, and put them really, really far away. You're looking there, you take an operator here and you take the other one on the moon. Now, I find that they're correlated with n equal to psi naught squared. But what I would like to be true is that as R goes to infinity, that this is equal to question mark. Is that equal to a factorized expectation value? You want to work in a theory where this is true. Why should the operator expectation value of this field here depend on the field on the moon? It shouldn't really. If it does, it probably means you're not setting things up properly. So if you work in the canonical ensemble, each of these is 0 because they don't conserve particle number. And so this is very inconvenient. But if you work in the right ensemble, this is non-zero, and that's great because this is true then. And that's what you want. So this is you want your field theory to be local, and you can make it local by not worrying too much about particle conservation number, or more precisely, breaking the symmetry. It's easier to break the symmetry explicitly rather than always remembering that the symmetry has to be restored eventually. Okay, so that's just we'll say more about this, but that's just a basic lesson in broken symmetry and what is the BCS state, what is a superconductor, and what's a superfluid. Questions? Yes, Juven.
Thank you. You noticed. Sorry, stupid question. So the psi here is fermionic.
This psi C is bosonic.
Oh, the psi
It's the
here.
product of two fermions.
No problem.
Psi C is bosonic. Psi without any C is a fermion. Correct. This is a fermion.
I saw for your notation, you have some kind of a big psi.
I'm sorry. These are all big psis.
Big psi, right? Yeah.
These are all big psis. I put a C, but I didn't put the big.
Yeah. Okay. And so those big psi is also gauge invariant. If I start from a U1
No.
gauge theory.
At the moment, let's not talk about gauge symmetry. They don't have any gauge fields. We only have a global symmetry, and they have a charge under the global symmetry. Yeah. So this expectation value, if you had a fixed number of particles, this expectation value would be 0. This would be 0. But I just go back to the previous chapter. We were talking about bosons. We had no trouble in thinking about B as a complex number. B0 we just say is a complex number because we don't care about how many particles in the condensate. This is exactly the same thing. We just think of psi C as a complex number. The this quantity here is the expectation of psi C as some number which tells you something about the condensate of pairs of fermions.
So both operator, also the product of these two operators, each of them also should be invariant. Sorry for using the word, but gauge invariant when they have gauge field. I don't know whether these are proper thing.
Yeah.
I just wonder whether they are being connected.
You're talking about this quantity.
Right.
Yeah, of course, if I gauge it, there will have to be a Wilson line between them. But right now, I'm only talking about global symmetries.
Okay. So that's what I want to ask. Is there a Wilson line connect them? And the answer is yes.
Once you introduce a gauge field, you do have to introduce it. Yes. We'll talk about that soon.
Thank you.
Okay.
Can I
All right. So now, yes, go ahead.
Would this kind of argument also work for something like P-wave, or do we have to have like spin orbit coupling? It
will work for anything. Just some of the indices will be different. The argument is basically the same. So for a P-wave, this function G would have a P-wave form. It would be odd rather than even. And maybe you have to take both of these to be spin up rather than one spin and one down, and so on. So in general, you can imagine a more general wave function. Then you could put an alpha beta here, and this make it alpha and make that beta. And then by choosing G alpha beta, as we have a whole matrix of spin functions, which can be even or odd or have complicated symmetries. And yeah, the possibilities are endless, and there are books written on all the different possibilities for G alpha beta. For helium-3, there are many different possibilities because there it turns out to be triplet. Yeah, but the simplest case is what I wrote down, where G is an even function and it's up and down pairing. That's the most common and simplest case.
Okay, so given like actual material, like we can compute all possibilities and we choose the lowest energy one, or is there another way? Okay.
No, that's what you do. Of course, that's not so easy to find out what it is. I mean, often you rely on experiments to tell you what the form of G is. So G is like the Cooper pair wave function. Okay.
Thank you.
Okay, so now we're going to do a mean field theory. Yes, go ahead.
Question?
Yes.
So you said that we would like these correlation functions to factor.
Yes.
And you said it's related to like requiring locality.
I forget the right word for it. There is another word for it. It's I forget. Sorry, go ahead.
Cluster decomposition?
That's correct. Thank you. Go ahead.
I see. But there are cases, right, where this factorizability doesn't happen at very long ranges, right? I'm thinking like some, these exotic entangled phases of matter.
They're not of this type. I mean, these are local operators. When you have some string operators or something, which is typically what you have in entangled phases, then it doesn't happen. But it's not the case. I don't know of any case where this kind of cluster decomposition doesn't always happen. That you can always choose your ensemble in a way that it happens. If it didn't happen, I mean, you can work with it if it didn't happen. It just actually you'll find your life is much more complicated if you do that.
Okay.
It's sort of the same thing, trying to do BEC in a canonical ensemble. It's not easy, but you can get the same answers after a lot of integrals. You can do the same here.
Okay, got it. Thank you.
Sorry, since he asked, maybe I can just clarify further. Excuse me again. So the big psi is a Bosonian operator of a Cooper pair of two fermions.
Correct.
And suppose there's an original as a U1, either global gauge, preferably gauge maybe later. The issue of this operator should not be gauge invariant, but in the broken phase, broken down to Z2, each of the big psi and psi dagger, big psi dagger will be gauge invariant on the Z2.
Okay, Juan, you're getting into very advanced topics, and since you're also, you're not this course is for the students, so I'm going to just ignore that question. Thank you for your question, but I don't want to get into that now.
The comment, that was not a question. There's a comment. Just try to clarify.
Okay, thank you for your comment, but let's stick to the basics here. There's this model of fermions with short-range attractive interaction. That's all. Okay, that's what we're talking about. There's no gauge field. There's nothing. We're going to get to the Z2. All right. So this is some notes of mine. You can read it if you care. Basically, statements. All the statements are explained in a little more explicitly. All right. So now what do we do? Okay. So we want to. So what you can, as I said earlier, this is our trial wave function. Ultimately, yeah. Well, okay. This is our trial wave function. Well, let's take this one. Yeah, if we ignore the alpha betas, this is our trial wave function. So this wave function depends on g of k. So we'd like to determine g of k by some mean field calculation. And then we'd like to determine the excitation spectrum. Now, what will happen at the synthesis of BEC, the kind of sound modes that we found earlier will also be present here. But we won't really even bother with that because, we'll get to that eventually using the Landau-Ginzburg theory. But there are new class of excitations here, which are fermionic excitations. They basically correspond to breaking a pair. So you have found these pairs. Now in helium-4 or something, the electrons or the fermions inside helium-4 are very tightly bound, tens of electron volts. But here in a Cooper pair, the electrons are bound by much, much smaller energy, only a few milli-electron volts. And that's why we have to, it's a range of experiments, very relevant to consider the energy for breaking a pair. And the energy for breaking a pair in BCS theory typically turns out to be much smaller than the Fermi energy. Whereas in helium-4, it was exactly the opposite, where the Fermi energy is much smaller than the energy to break a pair. So this is what we want to work out in this opposite limit, where the pairs are weakly bound and strongly overlapping. Those two go together. If they're very weakly bound, they tend to be far apart, the two fermions. And so the pairs are really not independent. They're strongly overlapping with each other. So you would think that this is a very hard regime to work in, but it turns out there's also another simple calculation we can do, which was done by BCS to really calculate things quite accurately in the limit where the pairs are very weakly bound. So what did BCS do? Well, so we're going to take this Hamiltonian for the fermions. So this is kinetic energy of the fermions, and we're just going to take a bunch of fermions with the attractive interaction. This is minus U naught, and only for fermions close to the Fermi energy. Okay, we're just going to take some quasi-particles. We imagine we've done Fermi liquid theory, so Landau's done all the hard work for us, and we just have some Fermi surface here, and we've got a few quasi-holes and a few particles, and we're going to put in a weak attractive interaction between them. So in the days of BCS theory, this was already a big step. We all thought electrons repel each other. What do you mean by they're attracting each other? How can that be possible? And that really was, what something Bardeen and Pines and others had been working on earlier. They had figured out that in the presence of phonons, there could be a net attractive interaction right near the Fermi level. And that's why, we take this model. It's very much motivated by coupling to phonons, and omega dBi is some low energy which is the typical energy of a phonon excitation. Today, of course, we have many examples of superconductors that don't come from the electron-phonon coupling. And what is the origin of the attractive interaction? Well, that's a question of much debate. And there's quite a bit of understanding on different ways that electron correlations can lead to attractive interactions. But for now, let's just take this model, the BCS model. All right, so this is our Hamiltonian. And BCS showed that there was an essentially exact solution of this Hamiltonian in the limit where omega dBi was much, much smaller than the Fermi energy. So this is the limit in which the BCS theory becomes really exact. And we just ignore the interaction between fermions far from the Fermi energy. Okay, so how does that proceed? Well, it proceeds in a way that's really very similar to the Bogoliubov theory in the operator language. What did we do in the Bogoliubov theory? We just said, okay, just identify the condensate and replace it by a complex number. Just keep those terms. Keep terms to the lowest order in the condensate and be done with it. That's exactly what we're going to do here. And what is our condensate? Well, our condensate is this quantity here. That's the Cooper pair operator. This is our condensate. Why is that? Well, we already saw that here, right? In these notes. Yeah. So you can see from here. So let's write this in momentum space. So this, of course, just that. So psi dagger, the Cooper pair operator, psi Cooper pair, capital psi. Thank you, Juven. At k equals 0. The zero momentum, let's call this capital K, the zero center of mass momentum K equals 0 is nothing but sum on K, G of K, C dagger K up, C dagger minus K down. So this is good. We're going to replace this by a C number, some complex number, condensate. Now here, really, it's the sum over K that's strictly speaking the condensate, but we're going to take every one of these things, each one of them to be a condensate. And the advantage of that is we do it that way. When you do the variational calculation, we'll in the end pull out what is G of K. We'll be able to calculate it. So that's the basic idea. You just go ahead, just as Bogoliubov did, and just replace, take your 4 Fermi interaction and just pull out factors of C dagger K and CK. All right. So this is what you do. So you have this term here. I haven't put in all the labels. You just replace anytime you had a C dagger by a number. this is going to be our condensate, which we don't know what function of K it is, but anyway, replaced by a number, and conversely the other one. And then if you want to keep track of the total energy, what you realize is you got to subtract this out, because if I just did a naive expectation value of the whole thing, if I took the expectation value of the left-hand side, let me just write this out. So this is in purple. If I took an expectation value, let me put double lines on it. Then I took the expectation value here. For this whole thing, you want it to be equal to C dagger times CC. And you notice that to make that work out correctly, you got to subtract this. Okay, later on in the path integral language, we'll see a better way of justifying this using the Hubbard-Stratanovich transformation or completing the square. But for now, that's the way we're going to proceed since we're not doing path integrals. Okay, so you apply this transformation where you just put in the constant in this term. And when the dust settles, this is what you get. This is the famous BCS theory, or the BCS Hamiltonian. So now following BCS notation, I introduce these quantities called delta and delta star, which is the pairing amplitude, as we'll see at the fermion gap. You see energy delta will turn out to be the energy to break a pair near the Fermi level. So that's delta here, and so the delta just comes from the expectation value of CC. So this is the equation. So this is like the Pogolevov theory in the following sense. The Pogolevov theory had one parameter, B0, which is the condensate, and the B0 was fixed by taking the saddle point value of the 0th order term. Here it's slightly different. We have one parameter, which is delta, but delta is fixed by solving this Hamiltonian. So a little more complicated than Bogoliubov. In Bogoliubov, you had to solve the 0th order theory. You got all the condensate, and then you solve the excitations. Here we're going to do together in one step. We have a condensate which determines the excitations, but the excitations themselves determine the condensate. And that's the self-consistency loop that you get from this factorization method. Okay, so now it's just a matter of solving this problem. You can give this to a mathematician, say, here's a Hamiltonian, here's delta, determine delta. And that's what the next steps are. We'll get to that on Monday. More questions? So I hope I didn't scare you, Juven. Go ahead and talk as much as you want. But I just try to keep things relevant to the topic at hand. Any others questions? Okay, great. So I think we're all in good shape, and it's time for the weekend. Well, I guess there will be a discussion session tomorrow morning at 9, if you care to get up Saturday morning at 9. If not, I will see you on Monday, where we'll continue our discussion of the BCS theory of superconductivity.
Sorry, I have one question.
Yes, please go ahead.
There's this like statement you made that was like kind of philosophical, that like with the 3D like problem and Fermi surface, you can somehow get this 1D problem without a Fermi surface. Is this like a prescription for making interesting physics happen? This is like very general, but like
this turns out to be a general feature of metals, of Fermi liquid theory, that if you look at quasi-particles near a Fermi surface, well, they predominantly disperse, or in fact, they disperse only orthogonal to the Fermi surface. But, because by definition, the Fermi surface is a locus where the energy is constant. So this is a constant energy surface where the energy is equal to chemical potential. And so the energy dispersion must be orthogonal to the surface, just by definition of constant energy surfaces. So to 0th order, you can think of a Fermi liquid as made up of an infinite set of quasi-particles. You can think of the angle around the quasi surface. You can think of this as a label. Labels different quasi-particles, all of which move in one dimension. This one moves this way, that one moves that way, that one moves that way. So, and the quasi-holes also move in the same way. So effectively, it ends up looking like an infinite set of fermions with a relativistic dispersion because it's linear in momentum. So it looks like an infinite set of one-dimensional relativistic fermions. So that's a very crude low picture of the low energy excitations of any Fermi surface. It's an infinite set of relativistic one-dimensional fermions. And that picture is useful for some things. In particular, it shows you very quickly why an attractive interaction between them will lead to a bound state, no matter how weak. But that's just a picture, and now the calculation we're going to do in solving these equations, the analog of that question is, when is delta non-zero? So suppose U naught was very weak. Okay. U naught is the attractive interaction, so U naught is weak. When I solve this problem, I find that delta is zero. If that means they don't form a bound state, they don't pair, and the pair can't condense. But what we'll see when we solve these equations is that no matter how small is U naught, delta is non-zero. This will come out of the solution of these equations. So that's more formally doing what inspired Cooper to first start thinking about this problem. This is the correct way to do this, not the way Cooper did it before the BCS theory. But it gave the right feature, which is also present in this theory, that for some purposes, you can think of fermions around a Fermi surface as an infinite set of relativistic one-dimensional fermions.
So as a like kind of restricting what adiabatic continuity is, then like can you only allow interactions that are like repulsive and short-ranged, maybe after screening or something like that? Or
no, okay. So that picture of infinite set of one, it may not work. For many things, it doesn't work. It turns out to work for this question. And the only way to settle that is to do a real calculation, which is what we're doing. That's why I didn't spend too much time on that picture, because it's an approximate thing.
okay.
It's not even, I don't think that picture is even mentioned in Cooper's paper. He just did a calculation. I don't know what inspired him. He did a calculation that Landau should have done, but never did. And he found this feature. And today we can kind of roughly understand it. I was just trying to avoid going through Cooper's calculation. If you want to actually go through Cooper's calculation, that's here in the notes. I just didn't want to go through it. This is the actual calculation right from Cooper's paper that I go through here. You can read about it.
Okay, thanks so much.
Sure. But it doesn't really teach you that much. I presented the way I think the best way to proceed. Not the historical way, but by analogy with the Bose gas, thinking about the condensate and then doing factorization. I think that's really the best way to understand things. Other questions? All right. Well, see you, if not tomorrow, then on Monday. And there will be a first homework problem set that we'll put up on the website sometime this weekend. Okay, see you all.